Yeah, hello everyone. This is the continuation video on solid state. This is solid state part 20, and in this video I'm going to talk about defects in solids, imperfections in solids. So you all know that in case of crystalline solids, the constant particles are arranged systematically. If there is any deviation from this systematic arrangement, that deviation is said to be defect. That deviation is said to be imperfection. That deviation is said to be some irregularity. For example, if you take a NaCl, in case of NaCl, chloride ions are forming FCC lattice, and Na plus ions will occupy body center and also all edge centers. In fact, which are called octahedral voids. Na plus ions are present in octahedral voids, and chloride ions are forming FCC. That means they should be at a face center and corners. If there is any deviation, if there is any irregularity from this systematic arrangement, then that deviation is said to be defect. The deviation is said to be imperfection. So these defects are mainly classified into two types. They are point defects. Second one is line defects. But for JEE, we have only point defects. And these point defects are further classified into three types. And let us take the various classes of all these defects. So defects are also known as imperfection. So defects are basically irregularities in the arrangement of constituent particles. So if there is any deviation from the arrangement, systematic arrangement, then that deviation is said to be defect. And these defects are mainly classified into two types. They are point defects. They are point defects. Another one is line defects. So what is the fundamental difference between point defect and line defect? You can understand easily with the help of this figure. In case of point defect, the deviation is found only at one point. In the given crystal structure, the deviation is found only at one point. But in case of line defects, you can see this, you can observe this particular diagram. And here the line defects are the irregularities from the ideal arrangement in the entire rows of lattice points. It is not confined to one point. See, for example, we are expecting some particles here, but the particles are missing along this line, entire rows of lattice points. But for JEE, for all competitive examinations, we have only point defects. So the deviation is found or confined only to one particular point. So these point defects are further classified into three types. So they are stoichiometric defects. Stoichiometric defect means due to this particular defect, the stoichiometry of the solid is not affected. The formula of the compound is not affected. And non-stoichiometric defects, because of these kind of defects, the stoichiometry of the solid is getting affected. And one more thing we have, that is impurity defects. Even for JE, we don't have impurity defects. So we have a stoichiometric defects and a non-stoichiometric defects. But a brief discussion also we have on impurity defects. And these stoichiometric defects are further classified into Schottky defects and FRENKEL defects. So now we need to understand what are Schottky defects, in which kind of solids the Schottky defects are observed, and what are FRENKEL defects, which kind of solids show FRENKEL defects, and what are the differences between Schottky defects and FRENKEL defects. That is our discussion in this video. So point defects are classified into three types: stoichiometric, non-stoichiometric, impurity defects. Stoichiometric defects means they do not disturb the stoichiometry of the solid. They do not disturb the stoichiometry. And you can see point defects. These are further classified into three types, and we need to take a stoichiometric defects. First, let us take a stoichiometric defects. So basically, these are the point defects. These are the point defects, and they do not disturb the stoichiometry of the solid. Stoichiometry of the solid is retained. Hence, these are said to be stoichiometric defects. And other name of stoichiometric defects, these are also known as intrinsic defects or thermodynamic defects. Intrinsic defects are thermodynamic defects because of temperature. Sometimes these kind of defects are observed, and internal changes, and also what do we call at a temperature due to some temperature. And these are further classified into different types. So first, let us take a vacancy defects. See, the term itself gives the meaning. Vacancy defect, vacancy. So this is definitely due to the missing of some constituent particles. Some constituent particles are missing. Some constituent particles are leaving the lattice. Due to the missing of some constituent particles, some defects are found. Those defects are called vacancy defect. So some constituent particles are missing, right? So density is equal to mass by volume. Volume is not getting affected. Volume of unit cell remains the same. We are expecting in one unit cell there must be 4 constituent particles. Due to the missing, for example, one constituent particle is missing. Instead of 4, now there are only 3 particles. There are only 3 particles means the mass of the unit cell, what happened, decreases. Volume remains the same. Due to the missing of some constituent particles, mass of the unit cell decreases. Mass of the unit cell decreases means density will definitely decrease. Density, so these defects decrease the density of the solid. So unit cell volume remains the same. But due to the missing of some constituent particles, mass of the unit cell will come down. When mass of the unit cell decreases by keeping volume constant, density will decrease because density is directly proportional to mass when volume is constant. And another one is interstitial defects. Vacancy defects, exactly opposite to vacancy defects, interstitial defects. So these are produced when some additional constituent particles occupy the interstitial sites. Some additional particles are coming into the solid, exactly opposite to vacancy defects. In case of vacancy defects, what happened is some constituent particles some constituent particles are leaving the lattice, but some additional particles are coming into the lattice. All such defects are said to be interstitial defects. And we are expecting only 4 constituent particles, but some additional particles are coming into the lattice. As a result, mass of the unit cell, what happened, increases. Mass of the unit cell increases when volume is constant. If mass increases, density will increase. And here these vacancy defects and interstitial defects are shown by non-ionic solids. The very important point, vacancy defects and interstitial defects are shown by non-ionic solids. Metallic solids you can take. Metallic, for example, sodium, otherwise potassium metal, lithium metal, whatever it may be. These are shown by non-ionic solids. And how to understand this vacancy defect and interstitial defects with the help of this picture, you can see these are the constituent particles, and here one particle is missing. One particle is missing, so here one hole is produced here, and these kind of defects are said to be vacancy defects. And interstitial defects, if you observe interstitial defects, this is the additional particle. This additional particle is coming from external source, and because of this, mass of the unit cell increases, density will also increase. And these vacancy defects and interstitial defects are found only in non-ion. They are not found in non-ionic solids. So they are found in non-ionic solids. They are not found in ionic solids. They are found only in non-ionic solids. In ionic solids, we have Schottky and Frenkel defects. So let us get into the details of Schottky defects and Frenkel defects. So it is Schottky defects. In case of Schottky defects, these are due to the missing of equal number of cations and anions. Basically, Schottky defects and Frenkel defects are found in ionic solids. Let us understand Schottky defects. See, for example, if you observe this particular picture, and there is a systematic arrangement of constant particles. Here the constant particles are ions, cations and anions. And if you see at this place, we are expecting one cation to be in this place, but a cation is missing. And here we are expecting one anion, but the anion is missing. Here also one anion is missing. Here one cation is missing. So basically these Schottky defects are produced due to the due to the missing of equal number of cations and anions. Equal number of cations and anions. So cations and anions both are missing in same number, and if defect is produced in this way, that defect is called Schottky defect. Again, the ions are missing. Ions are missing means obviously density of the solid what happened decreases. Schottky defects, due to Schottky defect, density what happened decreases, and the stoichiometry is not affected because equal number of ions are missing, cations and anions same in number. The missing numbers, if you observe, they are both are same. And another important point, these Schottky defects are found in the solids which have high coordination number. High coordination number means coordination number 6 and coordination number 8. That is possible when the size of cation and anion are almost same. I'm not saying same. There is no much difference in the radii of cation and anion. So this is about the Schottky defects. So due to Schottky defect, density what happened? Decreases. We have another kind of defect in ionic solids, that is Frenkel defects. Frenkel defects are also known as dislocation defects. Dislocation. Now you can see how to understand these Frenkel defects. If you see, this is the systematic arrangement of constant particles, but here ions are not missing. Ions are not missing. Now, if you see here, we are expecting cation, one cation here, but that cation is migrating from this site to some other site. You can see the ion is migrating from one site to another site, and whatever. So here some deviation is observed from the systematic arrangement. We are expecting cation should be at that place, but of that cation, instead of being at that place, it is migrating to some other place. And the defects produced in this manner are said to be Frenkel defects. But here ions are not missing. Ions are not missing. Hence, the mass of the unit cell remains the same. Density of the unit cell remains the same. And these kind of Frenkel defects are found in the solids which have low coordination number. Low coordination number means, so the limiting radius. So low coordination number. So limiting radius of smaller ion to radius of bigger ion. Radius, if you take the ratio, that is limiting radius. And in case of Frenkel defects, the solids which are showing Frenkel defects, the size difference between smaller ion and bigger ion is more. There is a large difference. Coordination number is like 4. Such kind of solids will show Frenkel defects. And another important point you have to observe, and if you see this Frenkel defect, so this is the lattice site or original site of the cation. This is the original site, and this is the new site. And if you observe this particular Frenkel defect with respect to this original site, here we are expecting some ion at this place, but ion is not present here. So at this original site, this is said to be vacancy defect. At original site, this defect is said to be vacancy defect. And if you take the new site, with respect to that new site, we can say that is interstitial defect. So with respect to the original site, it is said to be vacancy defect. With respect to the new site, this is said to be what do we call a interstitial defect. But basically Frenkel defects, here this is migration of ion from its original site to some other place, and it does not change the density of the solid. And these are the examples generally which show Frenkel defects. And the very important point, so it's a previous mains question also. So AgBr, silver bromide, it shows both the Frenkel and as well as the Schottky defects. And this is about stoichiometric defects. Basically, we have four examples: vacancy defects, interstitial defects. They are shown by non-ionic solids. In case of ionic solids, we have Schottky defects and Frenkel defects. And non-stoichiometric defects and impurity defects will continue in the next video. Thank you. Thank you very much.